Welcome back. Let us set up the case and specify the boundary conditions. Right click setup and click edit in this workbench window. The model is imported in CFX preprocessor. We can see the mesh details here. You can click this and see the regions. This is the 3D region and these are the 2D regions. Okay. Next, under the simulation, there is a flow analysis by default, and next there is analysis type. Here if you double click, you can change the settings to either steady state or transient. As of now, let it be steady state. Next, by default, it has selected the existing domain. This is called default domain. We shall specify the boundary conditions and other parameters in the normal mode. Last time for flat plate case, we used quick setup mode. This time we shall use the normal mode. Okay, let us start. First, let us specify the material properties. Double click default domain. You can see the default domain chosen here, and by default the fluid is selected as air at 25 degrees Celsius. For this case, the fluid is water. Okay. The reference pressure for this case is 0 atmosphere. We shall specify all the terms in terms of absolute conditions. Okay. Now the fluid property is specified. Next, we shall go to fluid models. Here we have to specify the heat transfer option. It can be either isothermal or thermal energy or total energy. If it is isothermal, the whole domain will be having a temperature of 25 degrees Celsius. We will be interested only in finding the velocity profile and pressure profile, but the temperature will be remaining same here. But our interest is to find out the heat transfer rate and the temperature changes. So we can either go for thermal energy or total energy. We shall quickly see what is the difference between thermal energy and total energy here. There are two options for heat transfer in CFX. One is thermal energy and the other one is total energy. In thermal energy, it solves primarily the thermal, that is internal energy equation, and it neglects the potential energy or the work due to viscous dissipation or pressure work like compressible flows, and it is computationally cheaper. It is commonly used for low speed incompressible flows and heat transfer problems with low Mach number, that is less than 0.3, can be used under thermal energy. In terms of total energy, it solves for the total energy equation, that is including internal, kinetic, potential, pressure volume work, etc. And it is commonly used for compressible flows such as high speed gas flows like jets, nozzles, etc. And it is commonly used for compressible flows and cases involving shock waves. So for this case, we can use thermal energy and solve the problem. For other cases, we can use total energy to include all the energy content in the case. Okay, we shall go back to Ansys CFX. Let us choose thermal energy here. Okay. Next, we shall leave the other options by default. Click OK. The fluid domain is set up now. Let us specify the boundary conditions now. Right click default domain, insert boundary. We shall specify the inlet boundary now. The boundary type is inlet and the location is inlet. We shall come to boundary details. We can specify either normal speed or velocity components or mass flow rate or in terms of total pressure and static pressure. Okay, in this case, we shall specify the mass flow rate. As per the problem definition, the inflow condition is as per volume flow rate, that is 10 liter per minute, which is equal to 0.1654 kg per second in terms of mass flow. We shall specify this value in the domain. So the value is 0.1654. 0.1654. Okay. And the flow direction is normal to the boundary condition. Okay. If there is any change in flow direction, we can specify using this cylindrical or Cartesian components. Okay. Let us leave the turbulence intensity by default. It is at 5%. We shall not change this. Now we shall specify the total temperature. The inlet temperature is 15 degrees Celsius. We shall specify the same. Inlet is 15 in terms of Celsius. Okay. Here the velocity component is so low, the difference between total temperature and static temperature will be almost negligible. So we can choose total temperature at the inlet. Now click OK. The arrow is showing the inlet region. Next, we shall specify the outlet region. Right click default domain, insert boundary, specify outlet. By default, it has chosen the boundary type as outlet based on the name. Next, we shall go to boundary details. Here we shall specify average static pressure. Let it be 1 atmosphere, because we have to specify any pressure condition in the flow domain. We have specified the mass flow and temperature at the inlet At the outlet, we shall specify the pressure condition, which is 1 atmosphere. Now we can click OK. Next, we shall create the wall domain. Right click default domain, insert boundary wall. OK. By default, it has chosen the boundary type as wall. Go to boundary details. Here you can specify the heat transfer option to heat flux, because in this case a constant heat flux is applied and we are interested in finding the exit temperature. We shall choose heat flux. The value is 73.46 kilowatt per meter square. Therefore, we shall write 73460 watt per meter square. Click apply. The other options can be left as such. Click OK. Now the boundary conditions are specified here. We can even rename the default domain to tube or pipe domain. OK. Now we shall come to solver control. Double click here. You can choose the advection scheme as high resolution by default. I will explain about these settings in the subsequent lectures. We shall change the turbulence numerics to high resolution. Let the maximum iterations be approximately 400. OK. Next, we shall set the residual target as 10 power minus 6. OK. And let it be RMS, not the max value. OK. So these are the iteration settings and residual target settings. You can click OK. Now the boundary conditions are specified. Next, we shall create some expressions to monitor during the solver. Right click expression, insert, create a new expression. Temperature at the exit. Here you can right click and create some expressions in terms of functions. Functions location based. You can choose mass flow averaged of, right click here, variables, temperature. Go to T, you will find temperature. Temperature. At right click, physical locators 2D outlet. So we will be able to monitor this temperature at the exit as the solver converges. Click apply. OK. Now we can go to output control, double click this, go to monitor, click create monitor and choose a new monitor point. You can write temperature at the exit. We cannot use the same name here, so we can click OK now. Here in the option you can choose expression, right click here, expressions. The created expression will be shown here. We can choose this temperature exit. Click OK. OK. Now the case is set up. We can minimize this and go to solver manager. Right click solution and click edit. The solver manager is open. We can check the options one by one. By default, the solver solves the case with single precision. If you select this, it will solve the case with double precision. Let us check the differences between these two. Single precision uses 32 bits or approximately 7 decimal digits of accuracy, whereas double precision uses 64 bits, which is around 15 to 16 decimal digits of accuracy. This is commonly used to avoid round-off errors. Single precision can be used for simpler models, steady state flows, low speed and single phase flows, whereas double precision is used for complex flow problems. It enables higher numerical accuracy. Single precision can be used for low speed incompressible flows and also heat transfer problems with low Mach number less than 0.3, and it can handle coarse mesh very well, whereas double precision is used for high speed flows with very fine mesh and high gradients in the flow. Single precision uses less memory and double precision uses higher memory, and also it takes a lot of CPU time. Okay, for this problem we can go ahead with single precision. We shall uncheck this. Large problem option can be chosen if the mesh size is huge beyond 2-3 million size. It will optimize the memory allocation accordingly. For this case, we shall not choose large problem. In the run mode, you can choose local parallel. If you are having a cluster of machines, you can use distributed parallel. We will not go for that. We will use local parallel. So we can choose the number of partitions based on the number of cores available. If you have 10 cores approximately, you can use 8 cores for solving. You can leave 1 or 2 cores as spare. Okay, let us go to initial values. If you have any previous result file available, we can choose that as initial conditions here. You can go to initial conditions, specify this initial value and load the result file from this option. If you don't have, then directly you can go for automatic or none. You can uncheck this. You can use initial conditions to improve your conversions quickly, because if you have any converged solution already available, you can start from that point onwards and you can finish the case quickly. Okay, in this case we will directly go ahead with automatic and we will not choose any initial flow condition. Okay, now we shall click start run. The solver has started. Here we can see mass and momentum residuals which are getting converged. There are three momentum residuals, that is U momentum, V momentum and W momentum. The mass momentum is shown in red. They are overlapped here. Okay. If we come to the user points, the expression what you have created is shown here. We can see the exit temperature, it is getting increased. It will converge after certain number of iterations. Okay. We can pause and come back after a while. If you see here, the residuals has become almost constant beyond certain number of iterations, and when we check the exit temperature, it has become almost constant. So it started from 288 Kelvin and it has finally reached 338 Kelvin. It is almost flat. So we shall not run beyond this. We can stop the solver at this particular iteration, or we can go to tools, edit run in progress, click no. We need not create a backup file. The solver settings will open. In this solver window, you can go to flow, solver control, convergence control. You can change the maximum number of iterations dynamically. You can change it to approximately 320. We need not run till 400 iterations. Close this and save and quit. So at 320 iterations, the solver will stop. We need not wait till the iteration gets over till 400 iterations. We can see at 320 iterations, the solver has stopped. The results are saved. You can click OK and go to CFX post browser. We can close this window and go to Workbench. Here we can refresh the results. Okay, in the next lecture we shall see post processing of results in CFX post. Thanks for watching this video. I will see you in the next lecture.